Okay, good morning everyone. Today we'll discuss differentiation of function of several variables. We will consider vector valued function of several variables and we'll discuss differentiation. Okay, differentiation of functions of several variables. So that means we are considering a function f which is defined on some open subset where E is open in Rn. Okay. We have now a function which is defined on an open subset of Rn to Rm. Okay. So Rn is a vector space and Rm is also a vector space. We are considering that function. So first obviously we need to define derivative at a point, or what do we mean by a function is differentiable at a point. Okay. To do this, first start with the notion of differentiation for a real valued function or real variable, one variable. Okay. So let's say suppose we have a function from R to R. Okay. Then let's say x belongs to R. What do we mean by the function f is? So we say that f is differentiable at x if limit h tends to 0, f of x plus h minus f of x by h exist. Okay. And we so exist in the sense that it exists finitely. Okay. If this limit exists, and we denote this as by f dash x at that point. Okay. So derivative of the function at the point f dash x. Okay. Now if we rewrite this, so this is equivalently, we can write f of x plus h minus f of x is f dash x into h plus r of h, where r of h we will call is a remainder, where limit h tends to 0, r of h by h is 0, and we say that r of h is called the remainder. So r of h is a function of h such that limit h tends to 0, r of h by h equals to 0. Okay. Now that's the other way of saying that a function is differentiable at the point h. Now we can think if this x is a real number, obviously derivative at a particular point is a real number. But now we can think if this x is a linear mapping from R to R. Okay. So now think f dash x is a linear mapping what is that linear? Which maps h to h into f dash x. Okay. So we are considering f dash x a real number. So actually in every real number can be think as a linear mapping from R1 to R1. Okay. Or any linear mapping in R1 to R1, we already proved that it's of the form k into x or k into h form, the constant into h form. We already proved in our tutorial, correct? So that means, so there is a one-to-one correspondence. So there is an one-to-one correspondence between a linear mapping from R1 to R1 and a real number, or sorry, so that means for each linear mapping we can now think as a number, and similarly if we have a number, real number, we can think this as a linear mapping. Okay, so therefore what we can say in this new definition, or we can say that a function is differentiable at a point x. So we can now say that we say f is differentiable at x if there exists a linear mapping. So we are denoting that, denoted by f dash x, such that limit h tends to 0, rh by h is 0. So in place of rh, what we'll write? We'll write f of x plus h minus f of x minus this f dash x. So this is now your linear operator, f dash x into h. So by, so linear mapping, h means that's linear mapping which maps h to h into f dash x. Okay, and by h this is equals to 0. Okay, so this is our new definition, a new way of saying that a function is differentiable at x if there exists a linear mapping from R1 to R1 such that limit h tends to 0, f of x plus h minus f of x minus h into f dash x. So that is linear mapping acting on h. So this quantity by h is equals to 0. Okay, so this is a value, obviously this is a number in R1. So this is a quantity, that value, particular value at the point h by h is equals to 0. So that's a new way of seeing the function is differentiable at x. So, and obviously this value f dash x will be the derivative of the function. The linear mapping is now is a derivative of the function at the point x. Okay, so that's how we can rewrite the definition of derivative of a function of single real valued function of single variable. Okay, so let's see how can we extend to a function vector valued function but single variable. Okay, so let's say we have a function now f from R1 to Rm. Okay, so that means what? It's a single variable function, single valued function, not single valued, I mean vector valued function of single variable. So f is now a vector valued function of single variable. How we define in general? So if we again, let's say x belongs to R1, we say that f is differentiable at A, we say f is differentiable at x when we say if limit h tends to 0, f of x plus h minus f of x by h equals to 0. So it's a 0 vector basically in this case. So this is a general way we define a function. Now again we can think this as similar to this, again we can rewrite this as well. So you can rewrite f of x plus h minus f of x, then which is h into f dash x plus r of h. Okay, so we can rewrite This is zero vector. So although we are using this notation, it's little bit. So this is a vector. So this will be a zero vector. Although you notationally you have to think about that. This is a vector, so it will be zero vector, not a real number zero. Okay, so it's correct. It's not a zero in the sense. It's a zero vector. Which is a single, no, not a single variable. It's a vector valued function. This is a vector. This is a vector, and you dividing by a number. No, not derivative 0. Limit x plus h minus f of x by h. Oh, sorry, yeah. I made it. Sorry, that's my mistake. Yeah, this is not derivative. Yeah, it exists. Sorry. Yeah, actually I mean to say that minus if this, okay. So exist. Thank you. So this exists, and this is we are writing as f dash x. This is what we are writing as f dash x. So this is a vector. So this f dash x nothing but a vector y. Vector in Rm. Okay. Like what we did in a last time, we can again rewrite this. Okay. So by the way, we rewrite this way, and where limit h tends to 0, Rh by h is obviously 0 in this case. Okay. So again, this is a vector. Now it's a vector 0. Now again, obviously we can think. So because we can associate, so there is a one-to-one correspondence. There is an one-to-one correspondence between a vector in Rm to a linear mapping from R1 to Rm. So because there is such a thing, so we can think a vector is now a linear mapping. So we are now thinking that f dash x y. So think this f dash x, which is y, as a linear mapping which maps h to what? Y into, so f dash x into h, or y into h. So this is your linear mapping. Okay. So it's a mapping from R1 to Rm. So therefore, if we think a vector as a linear mapping in this case, so what will be our new definition? So we can say the now, so we can say f from R1 to Rm is differentiable at x belongs to R1 if limit h tends to 0, f of x plus h minus f of x minus h into f dash x, or f dash x operating on h, so whatever paper you want to write, divided by h, which is equals to 0. Okay, that actually that time I want to write it, but somehow, okay, anyway. So this is will be equals to, this is your R of h by h is equals to 0. Now if you look at the numerator, it's a vector in Rm. Now we are dividing by a constant 1 by h. This should be equals to the 0 vector. Okay. If this limit exists, so we can say that the function is differentiable at a point x, and the derivative of the function is the linear operator f dash x. So now therefore our f dash x is nothing but a linear mapping from R1 to Rm. Okay, if you have a doubt, you can ask me directly. Yeah, f dash is the derivative of the function at that point x. No, a function is differentiable at a point, and f dash x is the derivative of the function at that point. So f dash x is a number, and in the number, in the sense, in this case it is a vector. So we are saying that vector is nothing but we are associating a vector. Actually, there is a one-to-one correspondence. We observe that there is an one-to-one correspondence between a vector in Rm and a linear mapping from R1 to Rm. So therefore, you can think a vector as a linear mapping from R1 to Rm. So therefore, derivative of a function at a point x is now a linear mapping from R1 to Rm in this case. Okay. So it's a linear mapping. It will be a linear mapping. Okay, it's a little bit new thing for some of you, so it will take some time, but when we'll see some example in the tutorial part, you will be more familiar with this. Yeah. That's a definition. Forget about if and only. That's how we are defining it. But it's not previously defined. This is the definition. We are defining it this way. Ah, that's not the finding thing. No. This is in this. When you read this, don't think that f prime is something already defined. F prime is just notation. And this is the note. You can just call it pfx. If there is a function pfx, so I am satisfying because I am making it as p naught. Yeah, right. Yeah. So I line from the head to f prime. Correct. So how do I explain the line? Ah, that's a different, it's a mechanical procedure. But this is the definition. So because we start with, from the childhood, we start with fx equals to sin x and derivative is cos x minus, cos x. So we think that, okay, this is a function. That's not the thing. You have to define it, and then we'll see that f dash will be a function. Let me come to that point. Okay, so that's how we define the differentiation of a vector valued function of single variable. Now we have the main part. Okay, so this is the main definition. But before we make the definition, let me write down some notation. Okay, so notation will use a linear. Okay. Okay, just let me write it down. So we'll denote this Rm to Rm is the space of all linear mapping from Rn to Rm. This is actually a metric space. Okay, so it's the space of all linear mapping or linear operator, you can say, yes, from Rn to Rm. Okay. So if n and m are equal, we will just use this notation Rn. If n equals to m. Okay. So this is the pace of all linear mapping because it will make us write thing in shorter term. Okay. So now we have the definition. So let E be an open subset of Rn. Okay. Let f from E to Rm be a function and x belongs to E. Okay. Then f is said to be differentiable at x, then f is said to be differentiable at x. So this is the definition we are writing, differentiable at a point x if there exist, if, that's a very important thing, it does not mean that it will exist. So if there exists a linear mapping, so there exists, let's say A belongs to Rn to Rm, so a linear mapping from Rn to Rm such that, okay, by the way, I just mean to say, so this is also can be written as, this is equivalently, you can take the mod value. Mod 0 equals to 0 also give you, now it will be a 0 number, okay. So you will get the same thing. So we'll use this mod as a definition. So if there exists an A belongs to R such that limit h tends to 0, mod of f of x plus h minus f of x minus ah, so A is acting on h, okay, so we'll just write sometime ah by h, this is 0. Okay. Be very careful. So in a numerator we have mod in which space we have this mod? In Rm, and this is a mod in Rn, okay. So otherwise if we don't take mod, so this has no meaning. So therefore we have to get this definition for mod, okay. So what we are saying that f is said to be differentiable at a point x if there exists a linear mapping. So because you are familiar with a linear mapping, nothing but a matrix. So we have a now matrix m by n matrix such that this quantity f of x plus h minus f of x minus ah, this whole quantity by h, this is going to be 0. If such thing exists, then we will say that function is differentiable at the point a. Okay, so in this case we will write case the derivative of f at x is denoted by dfx, or you can write f dash x. So now your dfx, a is your dfx, okay, or f dash x is your a. So in this case, so this dfx and f dash x, these are a, that linear mapping, and matrix m by n matrix, okay. So that's how we are defining function is differentiable at a point x, okay. So mod value of Rn is standard mod, what it is? So if h is a, let's say h1, h2, hn, then is square root of h1 square plus h2 square plus h, that mod, okay, not real number mod, okay. So you can also use the norm notation, that's fine, but it's, in the analysis we just use this way, okay. It's clear from the context. Okay. So, okay, also we'll say that this derivative also we call the total differentiation. This is also known as total differentiation to distinguish it from partial differentiation. We will soon introduce the partial derivatives. So this can be, think about the total derivative of f at the point x, okay. So be very careful because something new, so it's called total derivative. The total derivative of f at x is now a linear mapping. Linear mapping, so a matrix basically of order m by n, okay. Rm, okay. Good. Okay. So let's take a simple example and see what will be the derivative. Okay. Oh, by the way, so in our definition we take E as an open subset of Rn. So why we take in general open subset of Rn? Because we want to take a, such a way that x plus h should be an element of E. Okay, so to make that we just use that it's an open subset of Rn. But anyway, we define most cases in open subset so that this type of thing x plus h makes sense. Okay. Okay, let's say example. Let's say f itself is now your f itself is a matrix. That means a linear operator from Rn to Rm. So let f from Rn to Rm be a linear operator. So because we are using as a linear operator, okay, so what will be whether derivative at a point exists or not, we just want to know. Okay, so let's take a point. Let x belongs to Rn. Okay, so then you can see that then if we calculate f of x plus h minus f of x, because f is a linear mapping, okay, so you see that it will cancel out, you will have only f of h. So that means that ah part, this ah part, what we'll do, we'll take h by h. If we calculate this, limit h tends to 0, where a is now your f. If we take a as f itself, then what is the value we'll get? This will be equals to 0. So you see that if we have a linear operator, then the derivative, the function is differentiable at each point in Rn, and the derivative at that point is nothing but the function itself. Okay, so derivative at the point is the function itself. So in this case, so that means if f is a linear operator, then f dash x is f itself. Okay, so that means here. This is your f of h and a is f, so cancel out, it is becoming 0. So this proves that if we take a equals to f, then we are getting this value is equals to 0. And therefore this proves derivative at a point is the function itself. Okay. X plus, just a vector, sum of two vectors. It's Rn, na? X plus h. It's in Rn. Rn is a vector space. So two vectors, sum of two vectors. That's how we define. Okay. Fine. So that means tell me now if you are getting is, so if we have a matrix, let's say we have a matrix A equals to 1 0 0 0. Okay, what is the derivative? Find A dash of, so it's a matrix from R2 to R2. So what is the derivative of 0 0? A dash 0 0. Why is it is calling? So what will be the value of A dash at the point 0 0? No, it will be the matrix. So A dash 0 0 will be 1 0 0 0. The matrix itself. Derivative at the point will be the matrix itself. So in general, for whatever vector you will choose, xy, derivative will be the matrix itself. Okay. This is what we got. So derivative of the matrix at any vector is the matrix itself. So we choose only 2 by 2, but whatever matrix you will choose, if you calculate derivative, so derivative of the matrix exists. So if you have a matrix, it is differentiable, even it is zero matrix, then it is differentiable at each point. Still it is differentiable at each point, and derivative at that point is the matrix itself. Okay. Okay. You can ask me directly. Okay. Okay. It's look odd, but somehow it's like that. We are considering matrix is a linear mapping from R2 to R2 in this case, and then we are thinking about what is the derivative of the function at a point. Okay. So this is your vector, 0 by 0 is a vector in R2. Okay. Because we proved that if you have a linear operator, then derivative at the point is the operator itself. So because this is your linear operator, so derivative at a point, the operator itself. Okay. It's all cases, whatever linear operator from Rn to Rm, now a linear operator is nothing but a matrix from Rn to Rm. So therefore, yeah. So it's a, therefore it will be the matrix itself. Okay. Correct. Yeah, now if you consider Rn to Rm, you can think about the column matrix. Okay, because it will be a matrix of m by, okay, not it will be row matrix, m by n, row matrix. Okay. And the derivative will be that row matrix itself. Okay. It's like that. So is it more or less clear? Little bit. Okay. So now let's say if a derivative of a function exists at each point of u, so let's say f is a mapping from E to Rm, and E is a open subset of Rn. Suppose at each point x belongs to A, f dash x exists. So now let's say at each point function is differentiable. Yeah, yeah. R to R is also possible. So we can also think the same thing. No, not f of h. It is the f itself. That's the thing. It's a linear operator. It's not the operator acting on some vector. It's the operator itself. So derivative is an operator, not the value of an operator. Okay. So here your f dash x is now an element of Rn to Rm, the operator itself, not a vector itself. Okay. So suppose for each x, your derivative exists, then we have now a new mapping f dash from E to where? What to where? E to Rm. What will be the mapping? Now we have that function. Derivative is a function like fx equals to sin x, then f dash x is a cos x, that function. So f dash is now a mapping from E to what? It will be in Rm. What is the value? So it's take x to f dash x. This is the mapping. F dash takes x to f dash x. So f dash x is what? Is a linear operator from Rn to Rm. So this is a mapping from Rn to Rm. So f dash, you can think f dash as a mapping from E from Rn to Rm. Okay, that's the thing. So be very careful. This is also a metric space, actually, a non-linear space. Okay, I mean general metric space. Yeah. Now the question is, okay, okay, but there is little caveat over here. But what was? it will be a real number, but we are thinking a real number as a linear operator. Okay, just so that means multiply by that constant. So operator which maps taking any age, any real number to multiply by that real number. We are thinking that way. It's a 1 cross 1 matrix here in the. Let's say f of x equals to x. So the in general derivative at a point is now 1. So now 1 is your matrix. Matrix 1, just one entry 1. I forgot. 0. Possibilization. Which one? 1 0 0 0 is a function from R2 to R2. This is a part of vector space. Any linear mapping in a vector space from Rn to Rm can be think as a matrix of order m by n. Similarly, any matrix of order m by n can be think as a mapping, linear mapping from Rn to Rm. So that's how it's a function, and that's how derivative at that point is only point. Yeah, it will happen something like that. You will get a constant e to the power x, a derivative at a point. When you are calculating derivative at a point, you will get a constant. So you constant think about that as a matrix, a linear operator. What is the problem? Fx, your fx is e to the power x. So now we are calculating, let's say f dash 1. What is the value we will get? In general, it will be e. So this is your linear operator from R1 to R1. Because it's mapping h to e into h. It's a linear mapping in that sense. We already discussed, I mean, before I think you were not there. Before the starting of the lecture, we started. So any real number can be think as a linear mapping from R1 to R1. Okay. And any linear mapping from R1 to R1 can be you can think as a constant. Because any linear mapping is of the form constant into x. A linear mapping in R1 to R1 is nothing but a constant into x. We've already proved in a tutorial that if you have a linear mapping means it's a continuous function. So a continuous function from R1 to R1 is of the form f1 into x. Okay. That k into x we proved in the class. So that's how it is working. So it's a linear operator from R1 to R1. Okay, let me go. I will discuss more in the tutorial because let me finish. Otherwise, main thing we cannot cover. Okay, anyhow, okay. Ask me. We'll cover less. Maybe in tutorial we'll discuss more. What was your? Can you open it? I'll check. What is? When? Now? Open it. Okay. Okay. What was it? Yeah, total derivative we are defining a point. Even any derivative is defining we are at a point derivative. Then we have a function. Oh, it's changing. Don't do it. It's open. Okay. Okay. Any other question? Because we want to distinguish it from partial derivative. So we are saying that derivative as a total derivative. Okay. Okay. So f dash is now is a function from e to Rn to Rm. Now when I am saying it's a function from e Rn to Rm, what should be your first question? Is it well defined? When we are saying function, that means we are assuming f dash x is a unique number. But what's going on? But we did not prove that it's a unique. So the first thing we have to prove that derivative at a point is a unique linear operator. You cannot have two different values. Okay, values in the sense it's now a linear operator. Okay, let's try to prove this. Okay, so in shorter term, I just want to prove let A1 and A2 be two derivatives of f at x belongs to E. So we have it now same thing, f is a mapping from E to Rm, and let's say we have this x is now A1 and A2, both possible. Okay. So we want to show that then A1 should be equals to A2. Okay. These two linear operators are same operator. Okay. That's the thing. How to prove it? So proof is that, so let's say B equals to A1 minus A2. Okay. So obviously it's well defined because Rn Rm is a metric space. Okay. Or actually it's a vector space. So what is A1 minus A2 of x? Yeah, just a linear operator thing. Okay. So B is A1 minus A2. Okay. So then for H belongs to Rn, mod of BH is nothing but now A1H minus A2H. Okay. So this also can be written as f of x plus h minus fx minus A2H, then minus of f of x plus h minus fx minus A1H. Okay. Sorry, mod. This is your mod. Okay. Yes, rearranging this. Now by triangle inequality, this will be f of x plus h minus f of x minus A2 of h plus f of x plus h minus f of x minus A1 of h by triangle inequality. Okay. Now, therefore, if we consider BH by H, mod of H, okay, so two different mods, so we'll just take like this, okay. B of H by H, then what will happen? This is less than equals to mod of x plus H minus f of x minus A2H by mod of H plus f of x plus H minus f of x minus A1 of H divided by H. Now as H tends to 0, what will happen? As H tends to 0, you can see that B of H by H maps towards 0. Is it clear why it maps towards 0? Because A1, A2 are the derivative of the function at the point x. Okay. So now these two we prove. Okay. Now fix an H. Fix H belongs to Rn and H not equals to 0. Okay. Then B of TH by TH will map towards 0 as t tends to 0, because h is fixed but t is going towards 0. So obviously t which will map towards 0. So th by th will map towards 0. Okay. Now because b is a linear operator, but this b of th is nothing but t into b of h. Correct? Because b is a linear operator. So therefore b of th should be t into b of h. So that means what? T will cancel out with what we are getting. Therefore bh by mod of h should be equals to 0. Otherwise it is not possible, because this is a constant divided by a constant. So h is fixed. So constant divided by constant moving towards 0 means what? The constant itself should be 0. So that means bh should be 0. So this implies bh should be 0. So therefore b at any element, any vector h, it's becoming 0. And we know that it's a linear operator, so b of 0 is also 0. So therefore b itself is a 0 vector. Fix an h, okay, and h not equals to 0. Then we are taking t such that you have now th. So if t moves towards 0, so obviously th will move towards 0. So therefore you now we are using this fact. Something is moving towards 0, and then bh by this quantity should move towards 0. Okay. So now instead of h we are taking t into h. th is moving towards 0 as th is. What is going on? T moves towards 0 imply that t into h moves towards 0. Using that fact over here. Then cancel out t because it's a linear. So we have bh by h. Now bh is a constant. Mod of bh is a constant. Mod of h is a constant. So a constant moving towards 0. Therefore that constant should be equals to 0. There, but mod of h it's non-zero. So mod of bh is 0. So bh is 0. So therefore for any vector, non-zero vector it is 0. And because it's a linear, b of 0 is also 0. So this implies that b is equals to 0. This implies that a1 equals to a2. So derivative is unique at a point. So therefore it makes sense to define. So this makes sense. Okay. It makes sense. Okay. Okay. It's a little we are behind the time. Okay. Anyhow, we might cover something in tutorial as well. Okay. Previous slide. Okay. Okay. So usual algebra of derivative, like derivative sum of two functions. F is differentiable, g is differentiable at x, then f plus g is differentiable. Then all these things are well defined. Okay. So I mean it will work. So we're not going to prove. We'll just prove that it follows chain rule. Okay. So chain rule will prove only. Let me write down the statement, then we'll try to we'll discuss what it is. Okay, I hope that you know chain rule, correct? What it is? So composition of functions, correct? How to define. So here this whole as well. So theorem. Suppose again, suppose E is an open subset of Rn. E is an open subset of Rn and comma F is a mapping from E to Rm Okay, comma f is differentiable at the point x. F is differentiable at x naught belongs to E, and G maps. So G is a mapping. G maps an open set containing f of E, containing f of E into Rk, and G is differentiable at, and G is differentiable at f of x naught. So let's say y naught is equals to f of x naught. Then the mapping. Okay, let me erase this part. Then the mapping, composition of mapping is well defined because I'll discuss. First let me write. Then the mapping f of E into Rk. What's going on? Okay. Into Rk is differentiable at x naught, is differentiable at x naught, and so, well, let me write down mapping defined by thing. Defined by f of x equals to g of f of x is differentiable at x naught, and derivative at that point is g dash f of x naught into f dash x naught. Okay, so now I have to mention what we mean by product of. So this is a linear operator because derivative is a linear operator. F dash x naught is a linear operator. What do we mean by product of two linear operator? Okay, so how we define product of linear operator is just a composition of two mapping. Okay. Okay, let's see why it is so. So in general, okay, by the way, let me discuss then, we'll discuss what we mean by product of two linear operator. Okay. So we have an open set. So let's say we have an open set and we have a mapping form. F is a mapping from E to Rm, and there is a point x naught. Okay. Corresponding to this, you have a point f of x naught, and G is a mapping which defined on an open set containing the image of E under F. So it's containing, therefore, the composition mapping is well defined. Okay. So instead of defined on whole of Rm, G is defined on an open subset of Rm but containing f of E. So G is, let's say G is defined on some set G to Rm Rk, where f of E contained inside of G and G is open in Rm. So now we are saying that if G is differentiable at this point, so G is differentiable at f of x naught. So G now mapping G to G of f of x naught, correct? Then the composition of this, now composition mapping obviously will be a mapping from E to Rk. So that will be differentiable at the point x naught, and the value of the derivative at that point, that linear operator, is just a product of this linear operator. So remember this theorem. Product of this linear operator. It's like usual thing. But here you have, instead of product of two real numbers, now we have product of two real operators. Okay. So what do we mean by product of two real operators? So let's say we have a linear operator from a vector space x to y. Okay, or let's say A. A is a linear operator from x to y and B is a linear operator from y to z. Okay. Then we are defining the product. So this is the product of B and A. Order is important. First you have A, then you have B. What it is? This is defined as B of AX. So X belongs to X. Okay. So the composition of that is defined as a linear operator. Okay. The product. So clearly you can see that BA is not equals to AB. Even if we take X, Y, Z all as same thing, in general BA might not be equals to AB. Okay. But here in this case it is not possible if we have X and Z are different, X, Y, Z are different things. So that's how we are defining the product of two linear operators. Okay. Let's see whether it makes sense over here or not. So we have f dash x naught g dash f of x naught into f dash x naught. So f dash x naught is a mapping from where to where? F dash x naught is a mapping from Rn to Rm, correct? And g dash of f of x naught is now mapping from Rm to Rk. So obviously product makes sense. So therefore the product g dash of f of x naught into f of x naught makes sense. Be very careful. Here always you should have g dash f of x naught, f dash x naught. Do not write f dash x naught. If we write f dash x naught as f dash x naught into g dash of f of x naught, it might be correct in real number, but in general this is incorrect because the product A into B is not same as B into A. Okay, so do not make this mistake. Okay. No, it's a linear operator, not a single value. That's what we are discussing now till now. Derivative at a point is not a single value, it's a linear operator. So it's a linear operator from Rn to Rm, derivative at a point. Okay. So that means it's also acting on, so f dash x naught, taking a vector, when we write like this, then this is an element of Rm. This is a number, then you have a value. When you say acting on H, then you have a value. But in general, f dash x naught is just a linear operator. Okay, that's the thing. So this is incorrect. So we have to write in the other way. Okay, if we define that way, okay, I don't think we have time to prove this theorem. So I'm skipping that part. Okay, because I have to define partial derivative, otherwise we can't solve question basically. Okay. So now, till now what we have discussed is called notion of total derivative. Now let's define partial derivative of a function. Okay. Partial derivatives. Okay, let's say we consider the standard basis of Rn and Rm. Okay, by the way, we have a E subset of Rn, and if you have a mapping from E to Rm. Okay, so let E1, E2, En and E1, U2, Um be the standard bases of Rn and Rm respectively. Okay. Let's take a point x. Let's say x belongs to E and function is differentiable at x. Okay. Let x belongs to E. First, in general, if we have x belongs to E, then f of x will be an element of Rm because it's a basis. So you can write as a sum of this. So let x belongs to E, then f of x can be written as sum of, so constant, so I equals to 1 to m Ci into Ey. Okay, or j, let's say j. No, yeah, I will use notation I because j I use in different way. Ci into Ey. Okay, because it's a usual thing. Correct? Now this Ci will write this constant as summation I equals to 1 to m. Will write fi of x Ey. This Fix will be called the, so Fix, now you can think that Fix is a function from E to R. Is a function, it's a real number, Ci is a constant, so it's a real number. So function from E to R. So these Fi are called the component functions of F. Okay. So these Fis are called the component functions of F. Okay. So how to extract? So other way to define Fix, not that way. So if we suppose we want to define Fix, how will define instead of finding Ci? So if you look over here, your Fix, Fi from E to R is actually defined as Fix is equals to Fx into dot product with what? Suppose we want to get the Fix, so dot product with Ey, correct? If you take a dot product, you will get that Fix. So Fix at a point x is defined as Fx into dot product with Ey. Okay. For I equals to 1 to m. Okay. So actually we now have F, in general we write F as F1, F2, Fm. Okay. So these are your component function for F. Okay. Is it clear component function? So for example, if you are new in this area, so you know that if we write f of x plus y, let's say f is a function from R2 to R2 as x plus y e to the power x, then your f1x comma y is x plus y, this is your first component, and f2 of x comma y is e to the power x. So these are the component function for f. Okay. Clear? So it's a real valued function. These are real valued function. Okay. Now we are defining the partial derivative. The partial derivative, in general, we start with just define. Okay, let me just define first. Then we'll say define the quantity. We'll write dj fi of x. Okay, is equals to limit t tends to 0 fi of x plus tej minus f of x by t if exist. Okay. So in this case, if this limit exists, we will use this notation dj fi of x. What do you mean by dj for x? Limit t tends to 0, fi. So this function, so component function, for this particular component function, we are defining taking limit t tends to 0, x plus t ej. Okay. So that means what? If we write x plus t ej, let's say x is your in this form x1, x2, xj over here, and then you have n, and your ej is what? 0, 0, 0. You have 1, then again 0. Where you have this one? In the jth. Okay, that jth, what is called component. Okay, jth position or component or whatever. So then what is x plus tj? It is nothing but x1, x2, xj plus t, and then you have xn. This is usual. If you have a first order, second order, two variable, you have seen that we define how we define the partial derivative at a point, like with respect to x plus h. So how we define, let's say del f del x. Let's say f is a function of two variable. We just take limit t tends to 0, f of x plus t comma y minus f of x comma y by t. And how we define the partial derivative with respect to y? Limit, you can think about t tends to 0, f of x comma y plus t minus f of xy by t. Okay, so we are doing the same thing over here. Okay. Okay, so f is a function from where to where? R2 to R. This very careful. Then we can define. So that's why fi are function of real valued function. So that's how we can define that fi of x plus tj is this. So this is same. This we are generalizing to in the Rn to Rm space. Okay. So yeah, mod. No, it's a real number. Mod will be not there. That's what I said. That f should be a function from real valued function. So fi, this component are real valued function. So therefore it makes sense. Okay. So when this exists, we'll use this notation. Obviously, some other notation is del fi del xj. This is other notation we can use. This is different notation at a point x. Okay. Other notation you can use, and we'll say that derivative, partial derivative of x at the point x. I mean, it's difficult to say that way, but partial derivative of fi with respect to the variable j. Okay. Fi of x. Yeah, fi. Yes. Oh, sorry. Yeah, it is fi. Yeah, obviously it should be fi. Fi of x, not j. I mean, yeah, that should be obviously fi of x. Okay. So we'll just say that this is a partial derivative. We're not going to say the partial derivative of what and what, f and f, just a partial derivative. Okay. Function is x. Yeah, because we are defining on the component function. So that's why it's a ith component function with respect to the variable j. Yeah, so whatever I is running between 1 to m and j is running between, so this is defined for 1 less than equals to I less than equals to m and 1 less than equals to j less than equals to n. It just not all guys, one for one I and one j it exists. Let's say that particular partial derivative exists. Okay, so this will be called a partial derivative at the point x. Okay, and how many partial derivatives we have total? m into n number of partial derivatives you have in this case. Okay. So this is the thing. Is it clear how we define partial? Okay, you have a question? No, I should be there because f is a function from e to rm. So that's a vector valued function. But what we are defining for a real valued function. Okay. So partial derivative for the component functions. For a given function, we are calculating partial derivative for the component function. Okay. So every component you are so let's consider one component. Let's say f1. For f1, you are now calculating partial derivative of all x1, x2 in variables. For f2, you are calculating all n number of partial derivatives. So in this way, for each component function, you are calculating that many partial derivatives. Yeah. So now the question is how the derivative of a function related to the partial derivatives of all the components. That's the main thing because then we can use a partial derivative to get our derivative at a point. So we have to relate that somehow. The next theorem is that. Okay. So let me state the next theorem. Unfortunately, we are not getting time to prove it. But anyway, proof is simple, but we don't have time much. Okay. So theorem says that suppose f maps and open state E of Rn into Rm, okay, and f is differentiable at the point x at x belongs to E, then the partial derivative dj fi at x exists for all ij, exists for all 1 less than equals to j less than equals to m, sorry, n, and 1 less than equals to I less than equals to m. Okay. Moreover, this is the formula f dash x acting on ej, that standard vector ej, is equals to summation I equals to 1 to m dj fi of x, so partial derivative at the point, into ui. So obviously 1 less than equals to j less than equals to n, what it is. So this is the relation with, so it's saying that if a function has a total derivative at a point, then all the partial derivative at the point exist. Not only that, this is the relation. So this is obviously linear operator from Rn to Rm. Look over f dash x is a linear operator from Rn to Rm, and it's acting on Ej, you will get this value. So that means on the basis you know. So f dash of E1 will be this, f dash of E2 will be this, f dash of E3 will be this. Now we know that f dash is a linear mapping from Rn to Rm, so that means it's a matrix. So what will be the matrix representation of f dash x? So the matrix representation of f dash x will be, so let me denote by box of f dash x. What it would be? Because f dash x is given in the basis. So Rn has a basis E1, E2, En, and E1, E2, Em are the basis of Rm. So what will be the matrix representation? Yeah, so this will be first component. So this will be in the column, correct? So like D1, F1 at the point X. Okay. Then D1 at a point acting on D1, F2 of X. In this way, D1, Fnx. So in general, it's going on in this way. So Dj acting on F1x, Dj acting on F2x, Dj acting on Fnx, and then at the end, Dn acting on F1x, Dn acting on F2x, Dn acting on Fmx. So this is your matrix. If you take the derivative of this, not derivative, determinant, if we have m and n are equal, and if you take the derivative, then we have Jacobian, basically. Correct? Jacobian, we define Jacobian. So that is so. No. If total derivative exists, then partial derivative will exist, and the relation is that, and the value. Suppose you need to get the matrix representation. If you know the matrix representation, then obviously you know the function itself, and it's given by this formula. Okay, and this tells us that the matrix representation will be of this form. Okay. Partial derivative, the way we define the component functions. The way we define partial derivative, that for the component function, partial derivative exists. So we are not defining partial derivative of A at a point, but partial derivative of components of F at for the different variables. And the derivative, total derivative of F at a particular point now can be represented using the partial derivative of the components. Okay, and this is the relation. Okay, the converse is not true. If the partial derivative exists, it's not true that total derivative will exist. What is an example? So this is an example. F of xy is xy by x square plus y square if xy not equals to 0, 0, 0 if xy both are 0, 0. So even the function is not continuous. You can clearly see that limit does not exist basically, but the partial derivative will exist at each of that. Okay, so you can check it is so. It's a real value, although I took R2 to R1, but it's one example is enough to show that partial derivative exists but the derivative does not exist, total derivative. Okay, so it's your task to verify this. Okay, so okay, by the way, limit does not exist, you can clearly see that. If you put y equals to mx, what will happen? Limit x tends to 0, it will be x into mx by x square plus m square x square. So it will be m by 1 plus m square, and depends on the, it's not a unit, so limit does not exist, so function is not continuous. So if a function is not continuous, obviously it will be not differentiable. But the partial derivative exists, you can calculate it. Like if you fix an y and then calculate like that. Okay. Okay, now the question is, what about, suppose partial derivative exists, is there any other condition we can impose on it so that we can say that function will be differentiable at a point? Yeah, yes, there is a one extra condition. Okay, so here is the theorem. I think this is the last we can discuss. It says that There are two interesting theorems in this course. I thought that I will be able to discuss, but uh, because I will not get the time, because I also have to consider topological part. So I will finish today. So like inverse function theorem and implicit function theorem are two very important theorem uh, in this part. But okay, anyhow, we can solve some questions using this only. Okay. Okay. So what it is saying? Suppose F maps an open subset, an open set E of Rn into Rm, then F is continuously differentiable on E. So what do we mean by continuously differentiable on E? That means F dash, that function from E to Rn to Rm, is a continuous function. Okay. So if F is continuously differentiable function, if and only if the partial derivatives djfi exist, exist, because all need to have exist, and are continuous on E for 1 less than equals to I less than equals to M, 1 less than equals to J less than equals to N. So it says that on a set E, the total function is total derivative at each point will exist. Not only that, f dash is a continuous function if and only if all the partial derivatives exist on E and they are continuous on E. Okay, they should be continuous on the whole of E. Okay, then we have this region. Okay, so if we have a function where if all the partial derivatives exist and continuous functions, then we can easily say that derivative at each point will exist, and so obviously we can then write the derivative of a function at a particular point. Okay. So this is a interesting thing. So not only that, if you look at the last function, it will be that partial derivative at the point will exist, but that will be not continuous at the point 0 0. Okay, like x square by x square plus y square. Because of that, it will violate the. I mean, it will not going to satisfy this theorem. Okay. Okay, because we have a time a little bit, I will just uh, roughly speak what is inverse function theorem and implicit function theorem. Okay. So what it is saying, suppose we have a mapping from Rn to Rn. Okay. So like let's say F is a mapping from Rn to Rn. So F is a linear mapping. Okay. Then let's say we have a point A. So and we have a point A belongs to Rn such that F dash A exists and F dash A is differentiable. Sorry, it's invertible. Sorry. Okay. So let's say that means what it is saying. So suppose derivative exists at a point and the derivative is an invertible linear operator. Okay. It makes sense because it's from Rn to Rn. Okay. Then it is saying that function will be invertible in some neighborhood of A. Okay. Then f will be invertible in some neighborhood of A. Okay. What is the, how can we, so this, what is, why we need this idea? So think about that, we have a system of linear equations, okay, like f of x1, x2, xn equals to y1. Then, so how should I write? Let's say f of f1, f2, these are component functions, okay. So your f is now f1, f2, fn. Okay. So now if the matrix is invertible, you can have a solution. So suppose there is a point A which satisfies this equation, okay. Then it says that, and the derivative at the point means in this case, because it's a matrix, so derivative will be a matrix, okay. If this A is invertible means what? So we know that because F is a linear mapping, so it's a matrix. So derivative at the point will be the matrix itself. So that means if the matrix you get an invertible matrix, then you can write x1 in terms of y, correct? If y1, y2, yn are given, so you can write x1, x2, xn in terms of y. That's a very simple, I mean, you are already familiar with this. If we have a system of n linear equations of n variables, and if you take the coefficient matrix, if coefficient matrix is invertible, then you can find the solution. So inverse function is basically generalizing that thing, okay. So it's the same thing it's saying over here. Yeah, it will be f itself. Means that coefficient matrix you will get. F is invertible. Yeah, it will automatically true for every neighborhood of A. But in general, if we have like that, in general, suppose, I mean, I just put in a rough sense, but in general, we have something like that. If we have a mapping, continuously differentiable mapping which satisfy, not in general a linear mapping. I put in a linear mapping sense so that it makes, okay. But in general, if you have continuously differentiable mapping, then still you have this type. So instead of this linear equation, now we have the non-linear equation as well. Then if we have a non-linear equation and suppose there is a solution at a point, you have a solution and there the derivative is an invertible matrix, then it says that in that neighborhood of a point, that function has a solutions. Or you can say that if y1, y2, yn given, then xn can be written in terms of y1, y2, yn. Okay. So this is a, I mean, not the particular case of that theorem, okay, because don't have time to discuss the main thing like that. Okay. What about the explicit function theorem? What this says? I'll just tell you for the function of two variables but real value. But you can actually generalize. So implicit function theorem is given in a generalized case. The implicit function theorem says that so let's consider a function of two variables or real valued function of two variables. So like f of xy equals to 0. So you have some relation of x and y equals to 0. F is your continuously differentiable function. So f is a continuously differentiable function. Okay. Let's say there is a point AB for which f of AB is equals to 0. So let's say we have AB belongs to R2 such that f of AB equals to 0. Okay. Then it says that there will exist a neighborhood of B. Okay. So, okay, extra condition is that, and let's say del f del x calculated at AB not equals to 0. Okay. Suppose we calculate the partial derivative of f at the point x. Function is a real valued function, so you can calculate partial derivative at a point x, and which is not equals to 0. Then what will happen? So there will exist a neighborhood. There exists a neighborhood, let's say W of B, such that you can define, you will have a continuously differentiable mapping. So W to R2, not R2 R, like G of Y will be X. So you can explicitly write the function. So you can write G of Y equals to X. If we have f of xy equals to 0, suppose we want to write x in terms of y. So it says that if this condition met, if we have a function which satisfies this condition, then there is a neighborhood W of B where you can write x in terms of y. Okay. That's the one version of implicit function theorem. Similarly, if del f del y at AB not equals to 0, so there will be a neighborhood of A where you can write y in terms of x. Okay. So that's the implicit function theorem in a simplest case. But it has, obviously the standard theorem is more. Okay, by the way, G will be also continuously differentiable function. Differentiable function. Okay. So derivative, partial derivative is important. Why? Because here is your example. Consider this function. X square plus y square minus 1. So if we consider this equation, f of xy equals to 0, you see that put x equals to 1, y equals to 0, it will satisfy. So we'll take A as 1, B as 0. Okay. So that means it is satisfying. But what is the partial derivative of f at y with respect to y at 1, 0? It's 0. So it does not satisfy the condition. Okay. So you see that there will be no neighborhood of 1, 0. You can write x, y in terms of x. So y you cannot write. So let's say here you have, what is 1, 0 here? Here point 1, 0. So what we are saying, so there exists no neighborhood of 1, 0 where we can write y equals to fx, where f is a function, basically is a continuously differentiable function. Because whatever neighborhood you will consider, it will contain some negative part as well as real part. Because of that, you will not get the continuously differentiable function. Okay. Because whatever neighborhood consider, some upper part will be there. In general, what we can write, x square plus y square 0, y can be written as plus minus square root of x square minus 1, x square plus. So if we have x square plus y square minus 1, 0, so y square is 1 minus x square. So y is plus minus 1 minus x square. But because in 1, 0, you cannot write that way, basically. It's not coming properly. You see that? Both term will be going to be violent. Okay, so anyway, that's all from my side. But if you are interested, you can read implicit explicit function theorem, and obviously you will get question some competitive examination as well from whatever I discuss from analysis. I mean, especially from function of several variables. Okay, we'll discuss some questions in the tutorial as well. Okay. Any questions? Any question from the online participants? Okay. Yeah. Yeah. Then it's also going to be no. It will be non-zero. So there it will be okay, but there you are defining different way. No, it's saying that what is the theorem says? It says that it's talking about in a local position whether you can define a function in a neighborhood of B or not. Yeah, it depends on the choice of A and B. Okay. So it's a whether for defined point you have defined neighborhood, there might be possible to express. Okay. But for a particular point, it might there will be no neighborhood you cannot I mean where you can express. It depends on point to point. Yes. In this case, it will be neighborhood in R. Okay, okay, yeah, yeah. That's my. Oh, yeah, yeah, yeah. I made the mistake. W of this. So it should be neighborhood of uh, 1 comma 0. So it will be neighborhood of 1. Okay. So neighborhood of 1 means like, over here, not that one. Okay. So in this case, I will choose f del y. So it will be neighborhood of 1. In 1, you cannot express neighborhood of 1. Okay, I will see it later because. Okay, we'll meet again after 15 minutes. Oh, another thing is that okay, I did not fully written down the whole thing. You don't only not only you need a neighborhood of B or A, you also need a neighborhood of AB. Together will imply. Okay. So you also need a neighborhood of B such that also you need a neighborhood of AB. Okay. So both will together make sense. Okay. So I will explain it later.
Hello. Hello. Okay, so today we'll do very quick introduction as well as completion of ring theory. And we'll take up some problems in the tutorials. So that'll be more. So this will be what you already know. Okay. So just to establish conventions, because ring theory has many different conventions. Okay. So ring is a set R together with binary operations plus and dot on it that we call addition and multiplication. So I'm not writing all the signatures. It's just plus and dot of binary operations R plus R to R, such that R plus is an abelian group. That means we say that R on an abelian commutative group under addition. Okay, and we will denote its identity element by 0, as usual with additive notation, of course. Okay. And R dot is a monoid, so its identity will be denoted by 1. Again, 0 R or 1 R, 1 sub R when necessary, when you are discussing multiple rings. Okay, and there's equity as to which one you're talking about. And then the multiplication distributes over the addition from both sides. So again, we will not write that dot explicitly every time. So I'll just use juxtaposition to denote multiplication. All ABC. Okay. So when it's a ring, these are the things you have, and this is an obvious generalization of the most familiar example of integers. Okay, the most familiar arithmetic we have integers with the usual addition and multiplication. So this is just realization of that definition. But then, what else can we get from this that we don't have here? So, for example, and what is missing here that what is missing in the abstract definition that we have in the ring of integers? So one obvious thing is commutativity. So commutativity is missing. So ring in which dot is commutative, okay, or the multiplicative. So first of all, this R comma plus will equal the additive group, and R have a ring like Let me check. What is it? All this is yeah, is it audible from here? Can you? Yes, is it not audible at all? Audible. Is it loud now? Because I'm not sure which mic I'm using now, whether it's the loud. Yes. Okay, fine. So I'll continue like. Sorry about all the interruptions. Right. So commutative diffusion brings a field. Examples for these. Your usual familiar examples of Z or of course Q is there before that. C. These are all with the usual operations. These are all rings of which these three are fields. Okay. These three are fields. Now, if you have any ring R already, okay, then you can define the matrix ring over R as a set of all n by n matrices with entries in R with multiplication and division as defined usually. Okay, usual matrix multiplication and addition, except that when you multiply the entries or add the entries, that is happening in R rather than with real numbers. Okay. So in particular, we can take MN of R, that is a familiar one, right? Or you can take over any other field also. There are also have some special properties, but you can generally take over some big ones. Then what you need to be careful about here is when you try to do linear algebra with this, you need to define rank, dimension, etc. more carefully. In fact, it won't form vector space. It will form a module which will take some arbitrary ring. It form a module over the ring rather than vector space. Okay. So some of the definitions, usual definitions, may not work as they are. Okay. Another familiar example or common example is you can construct for any ring the ring of all polynomials with, for now, let's take single indeterminate x. Ring of all polynomials, that means all formal sums of the sum. Yeah. All formal sums of this form. Formal sum meaning that you don't have any other meaning for, say, x plus x to x, x plus 2x, or it doesn't evaluate to anything else. It is just an expression of that form, but with the multiplication and addition as defined usually for polynomials. Okay, there's a more formal way of defining this using functions, but the point is we can just define the formal assumption. Okay, it's a to work with. So this is the if R, if you take any ring R, so the coefficients of this polynomial, the coefficients of polynomial are these AIs, they are not from the ring. And therefore this will also form a ring. Okay, easy to verify that this R of x itself will form a ring under the usual addition and multiplication of polynomials. And will it what would be the identity element of this? The identity element of R itself. So if you can take n equal to 0 also here, no? So it will be just A naught. So A naught, when you take A naught equal to 1 of R, that will be the unity in this, that will be the identity element in this ring. In particular, observe that R itself is contained in R of x. Okay. A copy of R is contained in R of x. Again, because you can take the so-called constant polynomials where that n is 0. Okay, just A naught. So R is contained in this. Of course, actually, once you define subring, you can say it's a subring of R of x. Okay. But observe that it's contained in this. And then once you have this definition, you can easily define multivariate polynomials. How will you do that? Do you have to restart and again define it like this or any other way? Yeah, if you want a polynomial in two variables x and y, you simply define R xy to be R of x of y. Okay. Where this R of x is already a ring, no? This is nothing new. This part is nothing new. It is just you're in place of R, you're taking R of x and defining a new ring. Only you use a new indeterminate. Otherwise, it's not proper. You have to use a new indeterminate. But it's not that it's always defined this way. You will define this and this separately and show that they're equal. Okay. But for our use, we just define this way. So you can always define R of x1, x2, xn in the same manner by induction. Like because of your inductivity, you can define this. So multivariate polynomial ring, but this is commutative. Okay, I mean polynomials are not necessarily commutative, but this is called you are considering x and y as commuting with each other. Okay, you don't assume that x and y don't commute; they commute with each other. But you can also define non-commutative polynomial ring. That doesn't just mean that R is non-commutative. Observe that R of x is commutative if and only if R is commutative. R of x is commutative if and only if R is commutative. Similarly, when you define R of xy as defined here, again, if R is commutative, then R of x is commutative, and then by the same observation, R of x of y, which is R of xy, is also commutative, and vice versa, right? But you can specifically define something else, not this, something else for non-commutative polynomials, where these indeterminates don't commute with each other. That's a different definition. X and y don't commute with each other. So you can define it that way also, but that will be a different and not so easy to start. Anyway, just mentioning will not do anything with it. I think we have not looked at any example of finite rings. So what are the usual simplest examples of finite rings? Z mod rings. In fact, instead of Z mod rings, right? Which you can think of as Zn also. In particular, the smallest ring. Well, actually, there is the zero ring, not zero ring. The trivial ring. Sorry, get this confused. So this is the trivial ring where 0 is equal to 1. So usually we consider non-trivial rings because 0 is equal to 1. Many of things we talk about will not make sense. So usually for most of the results we consider non-trivial rings to make the exception. But this is also a ring as per our definition. Whereas when you define field, for example, you have to define field as, okay, I should be careful. It's a commutative ring. In fact, in division ring, right? And so I should mention that, yeah, you have to be careful. And 1 is not equal to 0. Then you call it a division ring. And that's a special case of field. So there we insist that it is not trivial. So a non-trivial ring, R, will form a division ring if all its non-zero elements are units. We form a field if it is commutative and division ring. So on. Okay. So this is a trivial ring. So the smallest non-trivial ring is say just 0 and 1. So the usual properties means 0 is 0 of addition and under multiplication will be absorbing and 1 is the identity of multiplication. Okay. So that is form and that is of course the what was it? Okay, fine. Yes. Any non-commutative, so this is one of the things that comes up in questions. What is an example of a non-commutative division ring? For example, Mn of R we took, right? So let's take in particular Mn of real numbers, R real numbers, not R any arbitrary real numbers. For n greater than 1, what can you say about this ring? R is commutative, you know. Real numbers, field, it's commutative, it's a field in fact. Mn of R, what can you say about it? It is non-commutative if n is greater than 1. Okay. So is this a division ring? Division ring which is I want a division ring which is not a field. That's the point. Is it? No, because it has some elements which are not units, which are non-zero but not units. For example, say 1 0 0 0 or 1 1 1 1 and so many examples. Okay. So in general, Mn of f if you take for a field, if n is greater or Mn of R also, but point is R itself may not be a division ring. But even if you take the field, even in that case, this will not be a division ring. So what is an example of a division ring which is not a field? So a non-commutative division ring. What is an example? Yes? Okay, let's try that. Suppose you take all matrices okay, so if you take this, I'll call it GLM of R. That's good. Is this a division ring? It's not a ring at all. is not closed under addition, right? For example, 1001 identity matrix. It is invertible, so it is there. 0110. It is self-inverse. Its square is identity, so it is invertible. So it's there. But what is this? All ones matrix, which is not invertible. Right? So what is the GLN of R? It's a group, general linear group. It's given in the notes, but I didn't discuss it in the text. It is GLN of R, which is a group. Okay, under multiplication, matrix multiplication, this forms a group, but not a ring. Okay, so yes, someone already told me. Quaternions, yes. So we saw the quaternion group, right? This was the quaternion group, which is of course not a ring. To form a ring from this, what do? You take X for Hilbert, no, Hamilton, sorry, not Hilbert. A plus B plus AC plus D. So define a linear combination of these things, the generators, not generators exactly, one comma I comma J comma K. So let's take linear combination of this, say A, B, C, D, and I. And define addition in the obvious way. What is the obvious way? If you take A1 plus IB1 plus etc., A2 plus IB2 plus etc., the term will be A1 plus A2 plus I times B1 plus B2, C times, J times C1 plus C2, and so on. Okay. How do you define multiplication? Meaning what? Usual means we don't know what to do with quaternions. So you assume that it's distributed because ultimately you want distributivity. So you multiply it pretending that it's distributive. Means you just distribute. But then you use the multiplication which is here. That is Ij is equal to K, Ji is equal to minus K, and so on. Okay. So you can actually carefully write down that expression and you'll get a big expression for the product. So even you know that even when you multiply complex numbers, so if you take just two complex numbers, which you can see is subset of this, correct? Complex numbers form subset when you take C equal to D equal to 0. Okay, when you just multiply complex numbers itself, that multiplication is complex. You get AC minus AD plus I times AD plus AC. Okay. That itself is not really easy to, it's not obvious what the product is going to be. You have to know, right? So here you get something even more complex. But you can write, you can do that. And that will definitely be why is it non-commutative? You have to write down the entire expression to check with like A plus IB plus JC plus KB and then some X plus I Y plus JZ plus WD and then multiply two ways and check whether it's commutative. Or simpler way, what is it? So just take a I and J. They are elements here. Because you can make A, C, B to be 0 or A, B, C to be 0. Right, and you get I and J. Ij is equal to minus Ji, not Ji. So it is not commutative. You don't have to take full expression and proof. Okay. Fine. Now to this is the ring of quaternions. Okay. And that is a non-commutative division ring. Of course, R is a subring of this. Okay. And C is also a subring of this. Okay. R and C are both subrings. R is a subring of C. It is a subring of H. Okay. Yes. Without the axiom, you know that. I mean, you don't have to assume it is the axiom. You know that 0x is equal to x0 is equal to 0 for all elements x. Okay. And minus. So that all works as usual. So minus 1 times A is equal to minus A, or more generally, minus A times B is equal to minus of AB. Minus A times minus B is plus AB, and so all these usual properties hold. Another thing is, suppose you take the set of all units of a ring. What structure does it have? Again, is it a ring? It is a multiplicative group. It is a group under the usual ring, under the same ring multiplication. It forms a group. Okay. So it is a subgroup of the multiplicative monoid of the ring. And we already saw an example of this. You take Mn of R in its multiplicative unit is exactly, unit group of, it's called the group of things. Its group of units is exactly ln of R. More generally, you take any ring you want, Mn of R, you take its group of units is defined to be ln of R. But its definition is not that the determinant is non-zero. So in ln of R, we for that R, real R, you just have to say determinant is non-zero. Here you have to say determinant is, if you want to pick these entries, you have to say determinant is. That's not it. Suppose R is, say, Z4. Okay, when you take a matrix A equal to okay, is this invertible in element of Z4? What is simple way of saying it? Once you take the determinant, what should it be? The determinant. So if you want to apply the usual formula does work. But for that, what is the formula? Aggregate A divided by determinant of A. That means aggregate of A will determinant of A inverse times aggregate of A. The inverse would exist. So determinant of A should be unit. That's it. If you take all the matrices whose determinants are units in that. So if you take R, then what are the units of R? I mean, capital, not capital, the blackboard bold R. Pairs. What are the units there? Anything that's not zero. In general, if you take GLN of F, then you just have to take determinant non-zero because any non-zero element of the field is a unit. Right. But you take some other thing, you have other possibilities. Like here, the determinant is 2, which is not easy. Okay. Okay, there are many other constructions of new rings from old rings. Okay. Won't go into all of that. Integral domain also went. So another thing where there are multiple conventions. Okay. Zero divisor of the language. R such that AV is equal to BA is equal to 0 for some non-zero element B. There are some conventions where A is also supposed to be non-zero. So you have to be careful. Anything when you read in ring theory, you really need to be careful about what conventions that particular book or paper follows, because there are different conventions. It's like reading graph theory, also where there are so many different conventions. Okay, so some textbooks like domain input take A also to be non-zero, to call it zero, non-zero, call it a zero device. So zero is not allowed. But most of the sentences work, I mean statements that we make work if we take zero also to be zero divisor. Because what is the meaning of zero divisor? Something that is a factor of zero, divisor of zero. That means that multiplied with something should be zero, something non-zero. That multiplied with something non-zero, that is definitely okay. This should be non-zero. So we also. So a ring, if uh, R has no zero devices, then R is bounded, and it is commutative. Okay. I'll actually make a different definition. Then R is a domain. Commutative domain can, I keep forgetting this non-trivial part. The non-trivial in R. Okay, we want 0 to be not equal to 1. The definition is really annoying, but we will always make that explain. So commutative domain with commutative domain is an integral domain. Actually, in some textbooks, say domain just for integral domain also. And there are even some textbooks where non-commutative one is also called integral domain. Yes. Non-zero zero. Sorry. Non-zero zero devices. Correct. Non-zero zero devices. Then it's that's right. Zero is already. So Z is a simple example. But any other examples? Every field is an integral domain. So another example, Z is not a field, but it's an integral domain. Any other example? Yes? Not Z. Z is a field. I want to integral domain is not a field. Z of X. Okay? Even R of X. Even f of X for any field. In fact, more generally, R of X where R is an integral domain. If you have one integral domain, again, if you take the polynomial ring, that will also be integral domain. And it's if and only. When only. Okay. R of X, so that's a useful result to know again for questions of let's R of X is an integral domain if and only R is in short forms. If and only if R is an integral domain. In particular, any field you take polynomial ring over that field will be integral domain. Can you give me an example of a finite integral domain that is not field? Any finite integral domain is a field. Why? Okay. What is another way to define integral domain? Integral domain is one where you can, what law holds? Cancellation law holds. Okay. So R is an integral domain when only as cancellation domain. Commutative non-trivial. Okay. Commutative non-trivial ring R is an integral domain if and only it has cancellation, which means what? Ax equal to ay a non-zero implies x equal to y. If a is any one element, such that non-zero element, such that ax equal to ay, then x equal to y. That's another way to define integral domain. Why is it true? Because if you have ax equal to ay, you can rewrite this a times x minus y is equal to 0. Then you know that a is not a zero divisor because it's not 0 and it's an integral domain. So you can say that x minus y has to be 0. Right, that's it. And vice versa. If you start with this property, you can again show that because a into 0 is equal to, suppose a into 0, not a, suppose a into b equal to 0. Suppose we assume this rather than that it's integral domain. So ab equal to 0 implies this is equal to A into 0. So if you assume cancellation, you can show that B is equal to 0. That means again that there are no non-zero zero devices. So cancellation implies that also. So it's equivalent. It's an equivalent definition. Okay. The cancellation is there. So then I say that from this you can immediately see that any finite integral domain must be a field. Right? Yeah, we already proved something in groups, which is finite. Actually, we didn't prove it, but we outlined the proof. Proved something stronger. Finite cancellated semi-group is a group. So here, if you take the multiplicative monoid, if you have finite integral domain, the multiplicative monoid is cancellation. Therefore, it must be a group, which means all the elements are units. Okay, so it must be an integral. So that's. There is another result. So here, by definition, you have commutativity. Okay. There is another result. Any finite division ring. What can you say about it? Is a field. Proof is not at all simple. It's a big proof. Better ones. So not simple proof. So homomorphism of rings. F from R to S is a homomorphism if f of x plus y, so we're not writing all the details. Guess what the unwritten quantifications are? This is any such function is a ring homomorphism. If you don't have this condition, okay, if you only have this, then it's a non-unital ring homomorphism. So if your rings are by definition non-unital, then that much is enough. Then you specifically call this with the third one, you call it a unital ring homomorphism if you have rings with unity. Okay, but yeah, I'll take this again as a definition. Right? So this has to be assumed. It does not follow from the first two. Right? If I just have the first two, the third cannot be in groups, for example, we don't need to assume this. We can prove it. Here we can't prove it from the first two. Why? Can you give me an example if you don't assume it? Yes. Because in groups, multiplicative inverses are there. Right. So if you assume that it's closed under multiplication, it preserves multiplication, then that has to be. Actually, yeah, that's it, because every element has an element. Yeah, that is enough. Here you can't do it. So for an example, you want a ring homomorphism between unity rings. It's not that the ring does not have unity. Suppose I take two rings with unity and define a function satisfying the first two properties. It is not a unital ring homomorphism. So what is an example? Satisfying the first two properties. Yeah. What is an example? Simple example. Okay, I'll tell you the rings. So then we can give you the example. Both are rings, right? Both have identity element because I'm taking Z itself. Okay, image is not a ring. Under my definition, the image is not a ring because the image of this is only even numbers. So the image of this set is 2Z. So it's not just that f of 1 is not 1. F of 1, that 1 is not even there in the image. Okay. Yeah, okay. So I have to assume the third one if I want the unit and ring thing to make sense. Okay, then once you have this, you can define image in the usual way, kernel in the usual way. Just that kernel is what? Coming from group theory, then don't make the mistake of saying that kernel is pre-image of 1. It is pre-image of 0. Okay, so kernel is pre-image of 0. Okay, so what is the property of the kernel? Kernel is an ideal. Kernel is an ideal of R. So we'll define ideal. Consider subset I of R is a left triangle if okay such that consider subset I of R which actually forms a subgroup under addition of the additive group. Then it's a left triangle if Ri for R comma E that you operation. Okay, fine. Alright. Ri is equal to I. You are working with non-unital things, you have to be careful. You have to say Ri is contained in it. Because it may not be equal. Because it's a unital ring, I can say Ri is equal to I. The actual condition in general, okay, so I will write that actually. I write it that way, because then you can generalize that to non-unital rings also. Right ideal I R is contained, right? And just ideal or specifically two-sided ideal if it is both left and right ideal. It's both a left ideal and a right ideal. It's a two-sided ideal. Oh, right. Yeah, you're that's correct. It does not satisfy the second problem. It is only a group homomorphism. It is not. It is not a ring homomorphism. It's not a multiplicity homomorphism. If n is equal to oh yeah, that's only one possibility. Take into 0. 10 to 0. Fine. Yeah, I think that is the only exception. I don't think you can get anything else, or unless at least in an integral domain, I think you can't get anything else. You cannot satisfy both of these. Okay, so when you go to 0, just like yeah, when you define vector spaces, you have that axiom 1 dot b is equal to b. If you leave out that axiom, you can almost prove it. You can prove that 1 dot b, if you don't have that 1 dot b equal to b axiom, from the remaining axioms, you have to prove that 1 dot b is either b for all b or it is 0 for all b. That can be proved. Similarly, here, I think not completely sure, right? Not very familiar with these examples. So, yeah, I think you can't get any other example. Thing that satisfies first two, but not. Let me think about it. Maybe tutorials I'll take it up if I get any example. Okay, so ideals are these. Fine, left ideal, right ideal. So in the case of unital rings, what we have, you are right, that you can just write Ri is equal to I. First, Ri is contained in I by this definition. Why is I contained in Ri? Because R has 1. 1 into I will be okay. Rotation also needs to be defined. Note by I have already defined for groups. So here also you define AB as what? We'll be careful. So by Ri here, I'll more carefully write it in terms of elements. Okay. So I'll write instead of just Ri is contained in I, LC for all R in R and I in I. R into I belongs to X. Similarly, I into R belongs to I for. And Ri and I are both. Two-sided ideal. Okay. Why? Because I didn't define that multiplication notation. But that's also not multiplicative. Because f of xy will be minus xy. But that's the problem. It's not a multiplicative number. F of xy is minus xy by definition. But f of x, f of y is minus x minus y, which is plus xy. So unless you have minus 1 equal to plus 1, but in that case, anyway, it's homomorphism. Because f of 1 will be minus 1, which is plus 1. Like if you take ring of characteristic 2, then it will work. But then it will also satisfy that problem. Okay, and think about it. So, fine, this is two-sided ideal. Now, if you have two ideals I and J, then I intersection J is also an ideal. I union J is not an ideal unless I of J is contained in J because it is not even a subgroup. We already proved that. But you have one more construction here. This IJ. Okay. So IJ is what? Finite sums of products of elements of IJ. Okay. So you take yeah, actually finite sums here because they are already ideals. That's it. Don't need linear combinations. Okay, finite sums of products of this form. One from I, one from J. First from I, second from J. That will be this set, and it will also be an ideal. Okay. So ideal notation is. So for ideal, we write. We borrow the subgroup notation and use the same thing. I is an ideal of R. For left and right ideal, if you want, you can use this notation. I guess I should use small L. Small L is okay, but capital L is okay, but yeah, that R is not at all related to this left and right. Okay, so ideal. So this will be an ideal, and so is. Again, you can test this with different conditions. Like suppose J is the right ideal, and I is an ideal. Then what happens? Then also this will be ideal. You don't need both I and J to be ideals. If J is the right ideal and I is the two-sided ideal, then again this will be ideal. Okay, that will work. So some things like that work. But generally we just use it when two-sided ideals there. So you have once you have ideals, and one more construction. So let me ask this IJ construction. Is it the correct analog of what we did for groups, subgroups, HK? HK we define. Is IJ the correct analog of that? No, because their group operation we were using multiplicative notation. If you use additive notation, you write H plus K. Here this I dot J, this I1 into J1, that is not a group operation. That is an operation in the monad. And then we are taking sum. So this involves both operations at the same time. So it is not at all similar to or it's not at all analogous to the group HK. Okay, that thing. I plus J is the correct one for that. So you take sum of the two ideals. Again, there are two-sided ideals. That will again be an ideal. Okay. Again, if I and J are left ideals, this will be a left ideal. I and J are right ideals, this will be a right ideal. Then, when you have ideals, you can define this. Good question. We'll do it in the tutorial. So, if you have R and I'm making an ideal of R, then you can define the quotient or factor or residue ring in the usual way. You take this as set of all x plus I, define addition and multiplication in the obvious way. So addition, this is all you know, it's already a quotient group because I is a subgroup and because the additive group is abelian, it's a normal subgroup definitely. So in quotient, you can find this as a quotient group for sure. And the group operation is addition, right? That's why you're using this multiplication. Normally we would write xx, but because the operation is denoted by plus, we are using x plus I rather. Okay. So this is just the quotient group. But you can now define a multiplication on it to make it a ring. What is that multiplication? So you consider this as subgroup of, you consider this as a group. Okay. In the usual way, with extra multiplication between. This way. So the ideal definition is exactly what you need to make this operation well defined. See, here for ideal, first you need, it should be a subgroup. And because R plus is commutative, you don't need to additionally say it's normal subgroup. It's automatically normal subgroup. That's an abelian group, right? So since it's a normal subgroup, you can definitely quotient by it. You don't need anything extra. Fine? But now we want to define multiplication. For this operation to be well defined, you need a other condition, the two-sided ideal condition. Okay. So this is called the ring of residues or quotient ring. Okay. Why residue? When you take Z, what are the ideals of Z? What are the subgroups of Z first of all? NZ. So ideals cannot be anything more. If anything, maybe some of them are not ideals. But actually, they are all ideals. So every ideal of Z is of this form. So you know it's a principal ideal domain. Every ideal is principal. Principal means like cyclic group, it's generated by one element. Only the definition is slightly different, but generated by one element. Okay. So when you take Z mod NZ, what do you actually get? 0 bar, 1 bar, n minus 1. But where this x bar means x plus z is notation. Okay. But what are these numbers? You know, etc. n minus 1? Yeah. The remainders that you get when you divide by n. Remainder as in residue. That's why it's also called a residue ring. Okay, a ring of residues. But we'll use a more familiar term, quotient or factor ring. Quotient field is something else. Even if R mod I is a field, you don't call it quotient field because that is a field of fractions. It's just slightly confusing terminology. That's why sometimes they don't use the word quotient for this. Because quotient field is like for Z. If you construct the field of fractions, that is Q, that's a quotient field. That is not at all Z mod anything. Okay. That is not at all Z mod anything. Okay. So that is a quotient field. So that terminology may be slightly confusing. Just keep that in mind when you read these things. Field of fractions are equal. Yeah, there is still time. So I literally split the fractions of it. They're just trying to call all the definitions and then do all the work to prepare it. Okay, when you define homomorphism, you can define usual thing, injective, surjective, isomorphism. Injective homomorphism is called embedding because it embeds the ring into, like you can find copy of that ring in the other ring. Right? You have an injective homomorphism from R to S, there's a copy of R inside S, which is the image of that homomorphism. Okay, so that's called embedding, as usual for any structure. Yeah, and then you have the isomorphism theorem also, so or induced mapping theorem. So if you have R, there is a canonical projection from R to R mod I, let's say it's 5. And then you have any homomorphism from R to S such that same thing as in Q, right? Such that kernel of F is contained in I is such that I is contained in kernel of F. Then you have any homomorphism, ring homomorphism from R mod I to S such that this commute, so such that F is equal to F star after 5. Okay. So 5. Now, suppose you have a ring R. You define a homomorphism chi from integer ring Z to R as follows. Well, write it here. It's 2. What is the meaning of N multiplied by 1R? One added to itself N times. In general, for any ring element, if you write some integer multiplied by the ring element, so not in the ring of integer, some other ring, if you multiply, write integer multiplied with the ring element, you're just adding that element to itself many times. Okay, so anyway, is this a ring homomorphism? Yes. We'll quickly check. So, m plus n goes to m plus n times 1R, which is, why is this true? Yes. No. Don't say this to me because this m and n are not elements of the ring R. This is not distributivity. This is just you look at the definition. What is m plus n R? I mean m plus n 1. 1 plus 1 plus m plus n times. That means m times plus n times. That's all. Not distributivity. Then not equal to this is maps to. Maps to. Okay. Mn maps to Mn 1R, which is okay. Me. This is chi of n. 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 For online classes. This is chi of n and this is chi of n. Here. Okay. Similarly, 1 maps to 1 of Zn, the integer 1 maps to 1 times 1, which is 1. Okay, so it is a ring homomorphism, unitary, right? what can you say about the image of this? Or what can you say about the kernel of this? Kernel is not necessary. No, not necessary. Because this is summary. I don't know what to do. This is summary. Kernel of prime is it is integral domain. No, R is summary, not integral domain. Even if it's integral domain, it may still not be. Can be integral domain, still kernel is not safe. Simply, it's just a definition. I'm not asking anything. Yeah? It has to be some kz. I'll say nz. Okay. Kernel, okay, it has to be some nz because it is an ideal of z. Kernel is an ideal. So ideal of z, you know this. Nz such that what? Such that n1 is equal to 0 and n is the least such. I'll just write n is minimal, meaning n is the least positive integer satisfying this. Okay. Least positive integer satisfying this. Because otherwise 0 satisfies it, that is need not equal. So this chi is called the, or yeah, that n is called the characteristic of R. Okay. And the image is the prime subring of R. It's just a name. It's just called prime subring. Okay. This image of chi is chi of z. Chi of z is called the prime subring of R. Now, when you have an integral domain, what happens? It is not true that integral domain kernel domain. For example, Z2 is an integral domain, correct? It's a field. Z2 is an integral domain. What is the kernel if this is Z2? 2Z. Okay. If R is Z2, Z mod 2, then kernel is 2Z. It's not 0. Right? Because it's characteristic 2. So it's somewhere in there. Even if you have a field, you can have a non-zero characteristic, right? But if it's an integral domain, you can say something about Z. What is it? I mean, sorry, something about n. N must be prime. So prove that also. Yeah, one thing to notice, this is isomorphic to what? That chi of z is isomorphic to Z mod n. Just note that the image of chi is isomorphic to Z mod of the kernel, Z mod n z. Okay. So in particular, that means when you have a ring of characteristic n, it has a subring. I didn't define subring, but you know the definition, right? Obviously. It has a subring isomorphic to Z mod n. Okay. Then you have the other isomorphism theorems, which I am not going into. So I just define rings. I'll define the ring of fraction and so on. Okay. I think with that we can do, and whatever else I will define. So take a commutative ring. R. And let D be a multiplicative subset of R. That means what? It is closed under multiplication. Okay. So multiplicative subset just means just use shortcut notation. Multiplicative which is closed. Okay. Okay, given the theorem of existence, but I'll just give it just a construction. So define P inverse R as follows. Sorry, just a minute. Ah, okay. Sorry, I think I lost connection for a minute. This is visible. Okay. Yeah, so I'll define what this means. Define D inverse R to be equivalence class of R comma D. Okay, where R comma D is from the Cartesian product of R and D, and you define the equivalence relation like this. Say R1 D1 is related to equivalent to R2 D2. So you can verify that it's equivalence. I'm not going to do it. If and only if there exists some P in D such that D times R1 D2 minus R2 D1 is equal to 0. Okay. Okay. Understand the definition carefully. You take the Cartesian product R across D, take elements from that, define an equivalence relation on R cross D as follows. R1 D1 is equivalent to R2 D2. If and only if there exists an element B, capital D, such that D multiplied by, it's not a function, multiplication, D multiplied with R1 D2 minus R2 D1 is 0. Fine. So basically, this is just R cross D modulo this relation. That means a set of equivalence classes. Okay. Then you can define operations on this as follows. So if you have R1 D1 plus class of R2 D2, how do you define this? Not R1 plus R2 D1 plus 2. R1, okay, let's go for a more intuitive notation. Okay. So, denote equivalence class of RD as R divided by, just use that notation. Okay, then define R1 over D1 plus R2 over D2 equal to R1 D1 plus R2, sorry, R1 D2 plus R2 D1. But to verify that all this is well defined, because these are all representatives, correct? These are all representatives of equivalence class. You verify that very carefully from this, and not difficult but tedious exercise. Similarly, you define R1 D1 R2 multiplied by R2 over D2 as R1 R2. With this notation, you can guess what this is, right? I mean, you just think of them as fractions. So the usual rule for adding and multiplying fractions, that's it. Okay. Fine, definition. Everyone? Okay. So then you can say that, you can see that any element of D can be identified with actually I'd say that R itself is in some sense means you can embed R into that unit. That will form a ring under the operation we define, and R will embed into it. So we'll just identify R with. So in the usual sense that integers are rational numbers, we say. Are they rational numbers? Rational numbers are defined as equivalence class of ordered pairs and so on. Right? So, but we identify integers with rational numbers. So in the same sense, elements of R can be identified with some elements of D inverse R, so that it becomes something like subring. Okay, sorry. That's all. The subring such that D is contained in the group of units. So every element of D becomes a unit in that U ring. Okay, every element of D becomes a unit in this U ring, and it is the universal object with that property. That means if you have suppose you have any ring homomorphism from R to some S such that the phi of theta is contained in the group of units of S. Then this is actually an inclusion. Okay, not literally subset or subring, it is an inclusion map. So with that inclusion, there is a unique homomorphism phi star such that again is converged. That is a universal property of this. Now, the particular case where R is a commutative, R is already commutative, R is an integral domain. Suppose R is an integral domain. You can take R to be, D to be all the non-zero elements of R. Okay. Then D inverse R will be a field. Because you know that D is contained in the group of units. But here D is all the non-zero elements. So all the non-zero elements of R will become units. In fact, this will be a field as well. Okay. And R will be contained in that. Okay. R will be contained in that. So D inverse R is a field. So yes? Smallest field. It is in fact that is actually from here. From the universal property, it is the smallest field into which R can be embedded. That is the same. That is the universal property. Okay, we'll stop. So that is the field of fractions. This is called the field of fractions or quotient field. Not a quotient in the sense of quotient equivalent. This field of quotients. Fine, thank you. Okay.